In this section, we'll study the theta method along with accuracy and efficiency. For the model problem, parabolic PDE, we considered the Ford-Euler method, and we studied about consistency and convergence and stability for the scheme. In this section, we'll try to discretize the time derivative different ways, and then we'll try to compare accuracy and efficiency. Let's see here. For the special discretization of use of XX, we are using this second order difference scheme, and we define A1, the operator, with negation of this term, and we formulated this semi-discrete equation. Now, for this semi-discrete equation, once we try to discretize this time derivative with a Ford difference, then it becomes the Ford-Euler method, and it is an explicit scheme given in this equation. So the triangulation error becomes this quantities. Now, rather than this Ford approximation for this time derivative, we may consider a little bit different way. The temporal discretization can be carried out in different ways. This one is backward scheme. Okay, let's see this. And we have, now that is n-1 time level, and this is now nth time level. This special discretization and right-hand side, the source is on this level. So that is the basic level and ground level, and this time derivative is approximated along with this way, and that is now the focal level, the basic level is nth time level, and this approximation is along with backward. Once we look at this level, then this level is in upstream, and so that the difference is a backward difference. Now, how about this one? This one is, now we are using in central level, and between these two levels, we are considering this level, so that is here t and minus 1/2. Okay, for this level, and we consider this special derivative and the source value on this level, and this difference will become central once we consider that we sitting on this level. Then this difference, okay, over there, over here, and the quantities are exactly the same. However, now this is the basic level is different, so that this becomes central difference, so that the time direction, the error will be second order. However, anyway, this one is not available during the computation. So that rather than using this one exactly, we may try to use this approximation. And on this level, the solution can be approximated by the average of below and top. So by using this one, replacing this quantity by this average, we can formulate the scheme. Then in this approximation, again, one more error will come out, but which is an order delta t squared. So it's small enough. So we can enjoy overall the second order convergence in time direction. Okay, that is observation. Based on this observation, we may consider theta method. So we can choose the basic level on the bottom, as in the forward Euler method, or any point here, any point, and that is half, and that is 1, so that theta is moving from 0 to 1. In this way, we try to formulate the theta method. Okay, let's see the theta method here. Given the observation, we define the theta method as in this formula, but that is time derivative and approximation and A1, and then now this is level, but here in any level over there, theta is moving from 0 to 1. It's not the value is not really available during the computation, so that by seeing this idea, we try to make linear interpolation between this value and that value for any level over there. For any theta, we are trying to use the linear interpolation between here and there. So in a sense, weighted average depending on theta. That's exactly this term. Okay, so that is a theta method. And here, right-hand side is also evaluated at the corresponding level. This can be rewritten in this form. First multiply delta t, and then manipulate unknown Vn to the left-hand side and known value to the right side. So we have this equation. When theta is 0, then that is left-hand side is Vn, and right side is 1 minus delta t A1 and Vn minus 1. That is exactly for the Euler method, an explicit scheme. And we already know that the stability condition requires this inequality. Mu is bounded by half. We already know that. Now, for backward Euler scheme, theta is 1, and we consider this one here, that is backward scheme. Now, the basic level is on the top, and we try to make this difference for time derivative. So it is backward approximation. And theta is 1, then from this equation, we can get here that equation. Once the theta is 1, that will disappear. And this is 1 plus delta t A1 and Vn. And you can get that one. Now, once you have this formula, then this is, in practice, a matrix. You will have to invert this matrix. Once that is representing approximation of u sub xx, and by using the second order scheme, then A1 will be a tridiagonal matrix. So you have to invert this one, but because it's a tridiagonal matrix, it's not so expensive. You can do it quite easily. And however, and along with this formula, you can choose arbitrary delta t. And even though delta t is large, it is stable. And for this algorithm, it's always stable. So we say it is unconditionally stable and stable independently of the choice of delta t, and so that it can be better than this forward-Euler method, even though in each step you have to invert a tridiagonal matrix. Now, when theta is 1/2, that is the case we considered in this observation, that one, along with this term replaced by this average. Okay, that is the case when theta is 1/2. And this is the scheme. Also, this scheme requires to solve a tridiagonal system in each time level. And however, this scheme is most popular because it is a second order in temporal direction. Of course, from the beginning, it is second order in spatial direction. Also, it is unconditionally stable as for the backward method. So it becomes very popular. And if you look at this case, that is called the Crank-Nichols method, and in the beginning, half step delta t looks like forward scheme. Okay, look at over there. And forward, this one step delta t forward scheme. Now that is half step forward and half step backward. That is one step backward, and this is half step backward. So it looks like halfly explicit, halfly implicit. So the Crank-Nichols method is sometimes called a semi-implicit method. Okay, let's see stability of the theta method. With f, the right side 0, the algebraic system, okay, for that one, I'm sorry. Okay, for this one, now point-wisely, we can write the detail. Then it becomes this one. So along with mu delta t over delta x squared, we can reach this equation for every point xj. Now, if we try to use the four-normal analysis, the first step is we can replace vjn with g to the n e to the ij theta. In the last section, we considered this technique. And then from this one, now first we replace and then divide by g to the n minus 1 and in e to the ij theta, then we can reach this simplified equation. And we can further simplify, and we can reach this equation. The amplification factor is given in this way. Now, mu is positive, and theta is chosen from this interval, so that is positive, that's negative. So here, this is always bounded by 1. Now, what we have to do is g must be larger than or equal to minus 1, so that the absolute value of g is bounded by 1. So what we have to do is this one, g is larger than or equal to 1. That one is the same as this one. And from this one, we can reach this inequality. Okay, that is the inequality. And now this value is between 0 and 1. So therefore, every theta, this must be satisfied. For the theta method, it is stable if this condition is satisfied. So earlier, we studied about the Ford-Euler method, which is now corresponding to theta equals 0. Then this inequality becomes mu is bounded by 1/2. That is exactly the stability condition for the Euler method, right? Okay. Now, theta is larger than or equal to half, then this becomes negative or 0, non-positive. And so that this inequality will be always satisfied. So that is exactly this comment. The theta method is unconditionally stable when theta is larger than or equal to 1/2. When it is 1/2, it is called the Kronecker-Nicolson method. And when theta is 1, it is called the backward Euler method. When theta is less than half, the method is stable. Okay, we rewrite, and for this term, we rewrite it and divide by 1 minus 2 theta, and we reach at that inequality. So when theta is 0, as in the Ford-Euler method, and mu is required to be bounded by 1/2 for its stability. For the Kronecker-Nicolson method, and it is really popular because it's a second order in both spatial and temporal directions, and unconditionally stable. Okay, let's see here, solve this problem. Now it is a little bit of perturbation of the example we earlier considered. Now we have here right hand side and initial values given in this way. For this PDE, the exact solution is given in this way. So it is increasing, but not so much faster. And this solution is increasing along with this function. And so that the solution will be reasonably good. It's slowly changing eventually. Earlier, in early example, the solution is decreasing along with e to the minus pi squared t. So it's rapidly decreasing, so that numerical error is quite observable. But for this problem, the error is relatively small. We want to solve the problem using theta method with theta 0, 1, 1/2, and we try to compare their accuracy and efficiency. Okay, we have here MATLAB code, heat equation, and 1D, and we try to solve that. Now, 0 and 1, this is domain, and last moment is 1 for the time direction, and that is the exact solution, and that is right hand side, and this is the initial condition. Now dx, nx is chosen 10, so that we can find the dx, and we made a grid point, and then now this is initial value, and here anti-forward is made in this way. That is, now once we are using Ford-Euler method, then the number of time steps must be chosen in this way. Once it is smaller than that, it may be blowing up, so that we will try to use this quantity. The exact solution at T1 can be found in this way. And here, now we are trying to solve the problem along with theta 0, 1, and half. Once the theta is 0, that is the Ford method, then we'll choose NT in this way. Otherwise, we try to choose NT twice of the number of points. and correspondingly now delta t and mu will be decided, and now theta much will be done, and at time 1 we have the solution, and we can measure the error and print out, and we try to get a figure. Okay, that's the algorithm. And this theta march is organized in this way. Now theta mu and 1 plus 2 the theta mu, and that is computed. And then now here, okay, we try to make matrix so that after getting this one, so here that B is representing this component. Okay, let's go back to the algorithm. Okay, that one along with the theta. Okay, this portion is now saved into matrix B. So after getting this portion and adding this source term, we try to invert to get the numerical solution at the nth level. That is organization of the function. Okay, so that can be made, and then now here in each time level, and fourth step can be done along with this one, and then here from V the right side is added, the source term is added, and then now we can get here the new solution. It is saved into a V0, and by using V0 again, next time level begins. Okay, that's the whole program, and we have this result. This one is now at times 1 now for theta method, and that is when theta is 0 and nt is 200. Now for this is backward Euler method, nt is now 20 and nx is 10, only twice, and also is 20 and along with the Kronecker-Nicolson method. For every method, the solution seems reasonably good. And as you can see over there, for the fourth method, once nx is 10, then for the method you have to choose 200 points, so that eventually mu must be bounded by 0.5. That is backward Euler. This one is now the Kronecker-Nicolson, and we have the error, corresponding error. And also when we define the mesh so that now nx is 20, and then you have to choose this number for the method to satisfy this stability condition. For others, now mu becomes very large. However, anyway, here it'll convergent so that you can get a reasonable solution. And again, one more time, refinement. Then for stability condition, for the Euler method, you have to choose this huge number of nt, and you can get the solution. Now, this backward Euler method, and because of only we are choosing and here 80 subinterval, so that error is large. However, anyway, it is convergent for Kronecker-Nicolson, and now the accuracy is better. To check the accuracy, now I changed the program a little bit slightly, and then I computed in this way. Now we keep the number point in special direction the same, 8 points, and so that the error, anyway, this error is coming from now order delta t, and this is 1 or 2, and now plus, and order now delta x squared. So that once we choose an x very large, then that will be very small. And then we try to check this component, assuming that that's small enough. We can check this error. So nx is 80, and here nt is chosen 10, 20, 40. But for the Euler method, for stability condition, and we have to choose this huge number of nt and to get the solution. And at the moment, the accuracy, the error is given in this way. Now, for backward Euler, 10, 20, 40 in time direction, and in this case, now mu is way larger than half, but now look at over there, error becomes half and half. Looks like really about half. So that means that the Euler method is first order in time direction. I'm sorry. I have a little bit of sore throat right now. Okay. Now, for Crank-Nicolson, the same way, we are trying to choose NT 10, 20, 40. And here, look at the error. And looks like here, way better than second order. But anyway, it becomes way smaller. It's quarter. If you multiply 4, then it's around there. If you multiply 4, so in fact this is more than second order. But anyway, asymptotically, the Crank-Nicolson method is a second order. And even though you are choosing only 40 points in time direction, this accuracy, this error is way smaller than this one. Even though you choose this huge number of points, you can get only this kind of the accuracy. Now, that is the first order, so that if you want to reach this level of accuracy, then you may try to define in time direction about 10 times, so that if you choose about 400 or 500 points in time direction, then by using this backward Euler, you can reach at this level of accuracy. So rather than this number of points, the time steps, you may choose about 500 points in time direction to reach at the same accuracy. If you want to use only first order in time, then the backward Euler may be more efficient to get the same level of accuracy. Now, for this one, Crank-Nicolson already with okay, this one, look at here about 20, and already it is reaching at this level, right? And when here the number of point is 20, so rather than more than 10,000, 12,000 time level, you can choose only 20 time level to get the accuracy. So in implementation and designing the algorithm, the Crank-Nicolson method is a little bit more complicated. However, eventually, this Crank-Nicolson method is way more efficient and way more accurate. Okay. Now here we have a summary. For theta method, when theta is 0, then error in time direction is first order. Of course, in spatial direction, for every method is a second order, because we begin with this second order approximation for spatial derivative. Now, for theta is 1, now we have a first order, And when theta is half, that is the Crank-Nichols method, the temporal accuracy is a second order. So the Crank-Nichols method is most accurate and efficient. In picture delivery, the core of effective picture delivery lies in balance between efficiency and accuracy. To get higher efficiency, they may deliver multiple pictures to similar addresses, but to enhance accuracy, they should verify those accuracies more carefully. And along with this, balancing picture delivery can be much more effective and successful. Life is also the same. You have to always try to keep balancing efficiency and accuracy. So from numerical method, you can learn a lot and for your future. Okay, that's the end of the section. Thank you.